Hey everyone, ready for a deep dive into some pretty cool number theory?
Yeah, should be a fun one.
We're talking Nahm sums, modular forms,
Warned
a conjecture that's been challenged recently.
Right.
We've got this paper, it's got some groundbreaking counterexamples. Get ready for some serious Q-series action.
It's going to be quite a journey. This paper, it really delves into the details of Nahm sums and how they connect to modularity.
Okay, so
The counterexamples, they really make us rethink what we thought we knew about a pretty long-held conjecture.
before we get too deep into the weeds though, let's make sure we're all on the same page.
Yeah.
Can you remind us what Nahm sums even are and why they matter in number theory?
Sure. A Nahm sum is a type of infinite series.
Okay.
We can write it like this. Math ABC TUES C1n plus PQ 1 and 1 plus CGQ. All of it is a complex number. Absolute value less than 1.
Right.
The matrix editor, it's positive, definite, symmetric times or Leving matrix, rational entries. And then robbers and tollers, those are vectors with rational entries. What makes Nahm sums so interesting is that sometimes they turn out to be modular forms.
Oh yeah, modular forms, those
Yeah.
supersymmetrical functions that pop up everywhere in math. What does it actually mean for a Nahm sum to be modular?
Good question. It means the Nahm sum has to have certain transformation properties under specific transformations. Like if you replace $dollar with, for some integer dollar,
Right.
the transform function can be written as a linear combination of the original function, just evaluated at different points.
Makes sense.
And this property links these sums to modular forms.
Which are incredibly important in number theory and other areas of math.
Exactly.
So in this paper, we're not just dealing with any Nahm sums, we're focusing on the ones that fit with Zagier's duality conjecture.
Right. Exactly. Zagier's conjecture, it basically predicted this beautiful symmetry within sets of parameters that make a Nahm sum modular. So we call these sets modular triples. We represent them as ABC. Right. So if ABC is a modular triple, the conjecture says that the dual triple ABC dollars is also modular triple.
So it's like a mirror image reflecting one triple into another.
Exactly.
I like that.
The dual triple is defined as A1, B made A1, B, C frac 1, 2, BT A1, B1.
And this paper, it dives into counterexamples to this
Yeah.
conjecture.
Yeah.
So where do we even begin with this paper?
The paper starts by talking about a classic example of modular Nahm sums, the Rogers-Ramanujan identities.
Ah, yes. The famous identities that connect an infinite sum to an infinite product. It's like mathematical poetry. Why are these identities so important in the context of Nahm sums?
They really illustrate modular Nahm sums perfectly. They show the connection between infinite sums and infinite products so beautifully.
Beautiful.
And here's what they look like. Sumti frau QTM frac Q dollar plus infti frau infi frei plus frac Q1 plus.
Look at all those q-hypergeometric symbols. For our listeners who might not remember, can you just give us a quick reminder about what those are?
Oh, of course. The q-hypergeometric symbol, we write it as AQNL. It's basically shorthand for a specific product of terms.
Okay.
It's defined as this. AQN1, 1AQ, where null can be any natural number or even infinity. Think of it like a chronologue of the factorial.
Yeah, okay, I see. Thanks for the refresher.
Yeah.
So the Rogers-Ramanujan identities, they give us a concrete example of modular Nahm sums. What comes next?
Well, inspired by these identities, mathematicians got curious. They started exploring what's known as Nahm's problem,
Okay.
which is all about figuring out all the parameter sets, the draw BC, that give us modular Nahm sums.
That sounds like a massive task.
It is. But Zagier, he made some good progress.
Okay.
He suggested specific conditions those parameters would need to meet for the Nahm sum to be modular.
That makes sense.
It was a huge step. But then, later, Vlasenko and Zwiegers, they found some counterexamples. And it showed that the world of modular Nahm sums is even more complex than we thought.
So even Zagier had his assumptions challenged.
It happens to the best of us.
What did these counterexamples actually tell us?
They showed that what Zagier initially proposed, those conditions, they were necessary but not quite enough to guarantee that a Nahm sum would be modular.
Interesting. So we needed to dig deeper.
Exactly. We needed a better understanding of when exactly these Nahm sums become modular.
And that brings us to page 2 of this paper, where we meet Mizuno's work. What did he contribute?
Well, Mizuno, he kind of took Nahm sums to another level. He introduced what are called generalized Nahm sums.
Oh, eh?
They include another parameter, a diagonal matrix D, positive integer entries.
So more complexity.
Right, and this generalization led to the concept of modular quadruples, which are represented as $, B1, B2.
Okay, so we've gone from triples to quadruples.
That's right. And on page 2, the paper gives a specific example. Uses a rank 3 matrix $, with vectors $, $, $, $, B, and a matrix $. And they show that while one of the generalized Nahm sums, the one built with these elements, it's proven to be modular, but others, specifically equations 1.9 and 1.10, are not modular.
So even within this generalized framework, we still have this mix of modular and non-modular sums. Some work, some don't.
That's right.
Like in cooking.
Exactly.
This feels like a direct challenge to Zagier's conjecture.
Right. It is. On page 3, they take Zagier's transformation, apply it to those quadruples, and they get what they call dual quadruples.
Okay.
And get this. They find a modular sum whose dual isn't modular. And even more surprisingly, they find non-modular sums that have modular duals. You can see these results in equations 1.1, 5.1, 1.4, and 1.1.
Wow, that's a pretty big crack in the foundation of Zagier's conjecture. What tools did they even use to get to those results?
Well, that's where theorem 1.3 comes in. It's the theorem that gives us the identities to prove those results about the dual quadruples. But to get to that theorem, they introduce something pretty elegant. A set of single-sum Rogers-Ramanujan type identities in theorem 1.4 on page 4.
More of that sum-to-product magic. Tell me more.
Oh, yeah. There are 4 of them, equations 1.15 through 1.18. They're beautiful, and they link directly to the world of Rogers-Ramanujan. They use those q-hypergeometric symbols, and they really showcase the connection between the generalized Nahm sums and those classic Q-series identities.
Okay, so we have these generalized Nahm sums, dual quadruples, and now these new Rogers-Ramanujan type identities all playing a part in disproving this conjecture. It's a mathematical symphony. Do they stay in this world of quadruples?
Actually, no. They go back to the original Nahm sums, those modular triples we talked about.
Interesting. What happens?
On page 5, in theorem 1.5, they have a concrete counterexample right in the realm of traditional Nahm sums. They show there's a modular Nahm sum whose dual, according to Zagier, should also be modular. But it's not. A direct hit to the original conjecture, not just the generalized one.
This is huge. We started with this elegant conjecture about duality, and now we're seeing it's way more complicated than that. But how do they actually prove all of this?
Well, that's where the heavy lifting starts. And trust me, it's a pretty fascinating journey through the world of Q-series manipulations and modular form magic.
I'm ready. Let's dive into those proofs.
The journey starts on page 6.
Okay.
They introduce this shorthand way of writing generalized Nahm sums, a function they call $5. They play with this function using substitutions. And then there's the Q-Gauss summation formula, and of course the Bailey pair method.
Wait, the Q-Gauss summation formula, I vaguely remember that from grad school. What is that again?
It's a formula that lets us simplify some types of infinite sums. It looks like this. Sum entity frac as MECBQ. It's super helpful when you're dealing with all those q-hypergeometric symbols.
Yeah, those can get out of control.
Yeah.
And what about Bailey pairs? Didn't they introduce some new Bailey pairs in the paper?
They did. In Lemma 2.1, they introduced 4 new Bailey pairs.
Wow.
These are key to proving those single-sum Rogers-Ramanujan type identities that we talked about.
Okay, cool.
It's like they're giving us new tools to explore Q-series with.
New tools for new discoveries. I like it. So they use these Bailey pairs, the Q-Gauss summation, some other Q-series wizardry to tackle these proofs. What else?
Well, to connect the Nahm sums to modular forms, they use something called the Dedekind eta function.
Okay.
Denoted by tau. It's defined as Q124 QQ infinity, where Q is A2 pi tau, and tau has positive imaginary part.
The Dedekind eta function. It's like a rock star of modular forms. I remember it has some special transformation properties, right? That make it super useful. How do they use it here?
Well, by connecting the Nahm sums to the Dedekind eta function, they can use the Dedekind function's modular properties to prove or disprove the modularity of the Nahm sums themselves. It's clever. It bridges the gap between these two different worlds.
So we have all these cool tools, Q-series, Bailey pairs, the Dedekind eta function. How do they all work together in the proofs?
That's where it gets even more interesting. To prove that certain dual Nahm sums are not modular, they use this technique called the constant term extractor.
Okay.
It's a way to pick out the term that doesn't have any powers of a certain variable from a power series.
So like extracting the essence of this series.
Exactly. It lets them write these Nahm sums in a form that just doesn't work with modularity. They show that these Nahm sums, when expressed with this extractor and with a certain identity, they violate those transformation properties that are like the hallmark of modular forms.
Wait, what identity?
It involves a function they call an innate error.
Remind me about that one.
Oh, it's defined using the q-hypergeometric symbol. And it helps them show that certain Nahm sums are not modular.
Clever.
Yeah.
So they're using all sorts of techniques and manipulations to challenge Zagier's conjecture.
Yeah.
But how do they get from those dual quadruples to the original Nahm sum triples?
That's in the concluding remarks, starting on page 12. They use a specific example with a set of numbers taken from a counterexample to the generalized conjecture. And they show why it doesn't directly translate to a counterexample for the original Zagier conjecture with the triples.
Right.
It highlights the subtle differences between the two.
So even though those dual quadruples don't directly give us counterexamples for the triples, they still find counterexamples within that original framework, right?
Exactly. They build specific examples, choosing certain parameters. They do the calculations, use the techniques we talked about to prove those examples violate Zagier's conjecture for the original Nahm sums.
Wow, this paper is a wild ride.
Mm-hmm.
Okay, so we've reached the last few pages. What are the key takeaways from those concluding remarks?
They really emphasize that even though they found these counterexamples to Zagier's conjecture, duality in Nahm sums isn't dead.
Okay, interesting.
They point to other research where duality still works. They suggest that maybe we need to refine our understanding of duality. Maybe we need more conditions or more subtle framework.
So it's not a complete rejection, it's more like a call for more exploration.
Yes, exactly. The paper ends with a really interesting question. What is the right way to think about duality in Nahm sums? It's a great invitation for more research. Who knows what we'll find out there?
Exciting. It feels like this paper has opened up a new chapter in the story of Nahm sums. But before we go too far down that road, can we take a closer look at the proof of Theorem 1.3? I think it deserves some more attention.
Of course. Theorem 1.3 is the core of their argument. It sets up those key identities that reveal those unexpected modularity results about the dual quadruples.
Can you remind us what those identities even look like?
Sure. Theorem 1.3 gives us 4 identities, equations 1.12 through 1.14. Each one involves generalized Nahm sums and their duals, showing those surprising relationships between them.
Right.
Some are modular, some are not.
And they use those new Bailey pairs from Lemma 2.1 in this proof. Right. How does that even work?
Right. They use the Bailey pair method, but with those new Bailey pairs, they start with an identity that we already know, and then they transform and substitute, manipulating the terms using Bailey pairs and q-hypergeometric symbols. It's really elegant, and it leads to those identities in Theorem 1.3.
This is all so complex, the amount of thought that must have gone into crafting these proofs.
It's amazing, isn't it? Math is so elegant and so deep.
Well, I'm definitely going to spend some time with these proofs later. I want to understand every detail.
They're worth it. But you know, this is really just the beginning. There are so many open questions about Nahm sums.
So much more to explore.
Exactly.
Okay, well, I think we've got a good job of diving deep into this paper. We've talked about Nahm sums, modular forms, Bailey pairs, the Dedekind eta function, and those counterexamples to Zagier's duality conjecture. What a journey.
It has been a fascinating look into a really exciting area of number theory.
And the best part? This is just the start. This paper, it's opened up so many new questions for mathematicians.
Oh, absolutely.
So if you're listening and you're interested in Nahm sums in modularity, this paper is a great place to start.
It is.
And who knows, maybe you'll be the one to figure out duality in Nahm sums and reveal the next layer of this incredible mathematical puzzle.
I wouldn't be surprised. There's so much left to discover.
Okay, well, that's it for our deep dive into Nahm sums. Hope you enjoyed it as much as we did. Until next time, keep exploring, keep asking questions, keep pushing the boundaries of what we know.
Absolutely.
All right, I've had a minute to process all that. So much to unpack. But now it's time to really dig into those proofs.
Yeah, let's get into the details.
So on page 6, they have this function, $5. It's like a shorthand way to write a generalized Nahm sum. Can you walk us through how they work with it?
Sure. The function $5, it lets them write those sums in a compact way. It's defined as FU1 QQZ sum n2 QKU $1. There's MPU and RPU.
Okay.
And they manipulate it using specific substitutions. Like they replace each WIO with Q, they choose the IS carefully.
Right.
And these substitutions, they help them express the function in a way that's easier to handle.
Okay, I see. So those substitutions simplify things. What about the Q-Gauss summation formula? Where does that come in?
Right. The Q-Gauss summation formula, they use that when they have to sum over certain indices.
Makes sense.
They apply it to parts of the function, and it lets them simplify those expressions with Q-Pockhammer symbols. It's like a shortcut, to navigate through the complexities.
Yeah, those Q-Pockhammers can be pretty messy.
Hmm.
And the Bailey pair method, where does that fit in all of this?
Bailey pairs are key here. They use them in a couple of ways. First, they have those 4 new Bailey pairs, remember?
Oh, yeah, and Lemma 2.1.
Right. And those, together with the Bailey pair method, they use those to prove those single-sum Rogers or Manoogian type identities.
Yeah, those were really cool.
Yeah. And the second way they use Bailey pairs is improving the identities in Theorem 1.3. The ones that show those unexpected modularity results for the dual quadruples. They combine the Bailey pair method with the new Bailey pairs from Lemma 2.1 to get those identities.
So Bailey pairs are like their secret weapon.
Haha, pretty much. And the Bailey pair method, it's really versatile. It's not just for this problem. It's a powerful way to explore Q-series and modular forms in general.
So they're building a strong case for those counterexamples. But what about the other part? Proving that some of those dual Nahm sums are not modular. How do they do that?
That's where they get really clever. On pages 7 and 8, they use a technique called the constant term extractor.
Okay, what's that?
It basically lets them isolate the term in a power series that doesn't involve any powers of a specific variable.
So like finding the core of the series.
Exactly. And it allows them to express those Nahm sums in a way that just doesn't fit with modularity. They basically show that those sums, when written using this extractor and a specific identity with that modular function, they break the rules of modular forms, those transformation properties.
Okay, you keep mentioning RQ. Remind me about that one.
Oh, it's just this function they define, using Q-Pockhammer symbols, of course, and it helps them prove that certain Nahm sums aren't modular.
Right, okay. Starting to all come together now. So they're using all these tools and techniques to challenge Zagier's conjecture. But how do they connect those dual quadruples back to the original Nahm sum triples?
Right, that's a good question. They talk about that in the concluding remarks. Starts on page 12. They take a specific example, uses numbers from a counterexample to the generalized conjecture, and they show that it doesn't directly translate to a counterexample for that original conjecture with the triples. It's subtle. There are differences between the two settings.
Right, okay.
But even though those dual quadruples don't directly give us counterexamples for the triples, they still manage to find counterexamples within the original framework.
Right.
They build specific examples, choose certain parameters, and then they go through the calculations using the techniques we talked about. And they show that these examples violate Zagier's conjecture for the original Nahm sums.
This paper is full of surprises. Okay, so we're at the end of the paper now. What are the key things to take away from those concluding remarks?
Well, they emphasize that even with these counterexamples, the idea of duality in Nahm sums, it's not completely gone. They point to other research where duality still holds, and they suggest that we might need a better understanding of duality, maybe with more conditions or a more nuanced way of thinking about it.
Right, so it's not the end of duality, just a new beginning.
Exactly. And the paper ends with a great question. What is the right way to think about duality in Nahm sums? It's perfect for future research. Who knows what's out there waiting to be discovered?
I feel like they've opened up a whole new chapter in the story of Nahm sums. But before we get too excited about that, can we go back to the proof of Theorem 1.3? I think it's worth a closer look.
Absolutely. Theorem 1.3, it's really the heart of the paper. It gives us those identities that show the surprising modularity results about dual quadruples.
Right, right. Can you remind me what those identities look like?
Sure. Theorem 1.3, it has 4 identities, equations 1.12 through 1.14. Each one involves generalized Nahm sums and their duals. And they show those interesting relationships between them, whether they are modular or not.
Okay, yeah. And you said they use those new Bailey pairs from Lemma 2.1 in this proof. How does that even work?
Right, so they use the Bailey pair method, but with those new Bailey pairs. It's really clever. They start with an identity that we already know, and then they transform and substitute, manipulating the terms using Bailey pairs and q-Pockhammer symbols. It's really elegant, and it leads to those identities in Theorem 1.3.
This is all so intricate and interconnected. It's amazing how they put all these pieces together.
I know, right? It really shows how elegant and deep math can be.
I'm going to need to spend some quality time with these proofs later, really work through them.
They're worth it. But this is really just the beginning. There's so much more to explore in the world of Nahm sums.
So much more to learn.
Oh,
Okay, well, I think we've covered a lot with those proofs. Anything else in the paper that you think we should take a closer look at?
one thing I really appreciate is how careful they are. They really pay attention to the details. They explain the differences between generalized Nahm sums and the traditional ones. They make sure their counterexamples are solid, and they apply to both settings. They don't shy away from the complexity.
I agree. They're very thorough. You can tell they really care about being rigorous.
Absolutely. And you need that rigor in a field like this. The concepts are abstract, the proofs are intricate. You can't be sloppy.
Well, I think we've done a pretty good deep dive into this paper. Nahm sums, modular forms, Bailey pairs, the Dedekind eta function, those amazing counterexamples to Zagier's conjecture. It's been an incredible journey.
I agree. A fascinating exploration of a really cool area of number theory.
And the best part, this is just the beginning. This paper has opened up so many new questions, so many challenges for mathematicians to work on.
Absolutely.
So to everyone listening, if you're intrigued by Nahm sums, by modularity, this paper is a great place to start. And who knows, maybe you'll be the one to crack the code of duality in Nahm sums. Maybe you'll find the next piece of this amazing mathematical puzzle.
I wouldn't be surprised. There's so much left to discover.
Well, that's it for our deep dive into Nahm sums. We hope you enjoyed it. Until next time, keep exploring, keep asking questions, keep pushing the boundaries of what we know.
Exactly. Keep that curiosity alive.
All right, let's dive into some more of these proofs. I'm really curious about those single-sum Rogers-Ramanujan type identities, the ones in Theorem 1.4.
Yeah, those are pretty neat.
They're so elegant. How did they come up with those?
Those identities are great. They really highlight that connection between the generalized Nahm sums and those classic Q-series results.
Can you remind me what those identities even look like?
Of course. So Theorem 1.4 has 4 identities, equations 1.15 to 1.18. They've got those infinite sums and products, all written with the q-Pochhammer symbols.
All right, those q-Pochhammer symbols are everywhere in this paper. I'm still amazed by how they connect those generalized Nahm sums to the Rogers-Ramanujan identities. It's like finding a secret passage between two mathematical worlds.
It is remarkable, and the secret to that connection, it's those new Bailey pairs from Lemma 2.1.
Ah, right. So how do those Bailey pairs help prove these identities?
Well, they start with a Bailey pair identity, one that we already know,
Okay.
and then they apply all these transformations, substitutions, they manipulate the terms using the properties of Bailey pairs and those q-Pochhammer symbols. It's a beautiful dance of symbols, and it leads to those elegant identities.
It sounds complicated. Are there any steps in the proof that really stand out? Like something especially clever or unexpected?
One really clever step, they use the Jacobi triple product identity. They apply it to part of that transformed Bailey pair identity.
Right.
And it helps them simplify everything, and it reveals that sum to product structure they're looking for. It's brilliant.
The Jacobi triple product identity takes me back. It's amazing how they combine all these tools to build these proofs.
It really is. It shows how deeply they understand Q-series and their ability to see connections that others might miss.
I'm definitely going to need to spend some time working through these proofs, really understand all the details.
Yeah, they're worth it. But, the Bailey pair method, it's not just for this problem.
Oh, right.
It's powerful. It's used all over Q-series research, and it keeps leading to new discoveries.
Okay, well, we've gone through a lot of proofs. Is there anything else in this paper that you think we should highlight?
One thing I really like is how thorough the authors are.
Yeah.
They're careful about explaining the differences between those generalized Nahm sums and the traditional ones. They make sure their counterexamples are rock solid and that they work for both.
They don't cut any corners.
Nope. They're committed to being precise and rigorous.
And that's important, especially in this area of math, right?
Oh, absolutely. It's essential. The concepts are abstract. The proofs are so intricate. You can't afford to be sloppy.
Well, I think we've done a pretty good deep dive into this paper.
Yeah, I think so too.
We've explored Nahm sums, modular forms, Bailey pairs, the Dedekind eta function, and those incredible counterexamples to Zagier's conjecture. It's been quite a journey.
It has. Really fascinating.
And this is just the beginning.
Right.
This paper opens up so many new questions, so many challenges for mathematicians to tackle. So to all our listeners out there, if you're interested in this world, in Nahm sums and modularity, this paper is a great starting point.
It is.
And who knows, maybe you'll be the one to unlock the secrets of duality in Nahm sums. Maybe you'll find the next piece of this incredible mathematical puzzle.
There's so much more to discover.
Well, that's all for our deep dive into the world of Nahm sums.
I hope you enjoyed it.
We had a blast, and we hope you did too. Until next time, keep exploring, keep asking questions, keep pushing the boundaries of what we know.
Keep that curiosity alive.
Welcome back, everyone. Today, we're diving into a paper that, well, it kind of shakes things up in the world of Nahm sums and modular forms.
Oh, yeah. It's a fascinating paper. It really throws a wrench in things.
So this paper, it's called Counterexamples to Zagier's Duality Conjecture on Nahm sums by Liuquan Wang. Before we get into the nitty-gritty, can you set the scene for us? What exactly is Nahm's problem? What's this whole duality idea about?
So Nahm's problem, it basically asks, can we find all those rational, positive, definite matrices A, vectors B, and scalar C that make the corresponding Nahm sum modular?
And just for our listeners who might need a quick refresher, a Nahm sum, it's a specific type of Q series, right?
Right.
And a Q series is a series where the terms are powers of Q. Sometimes these series turn out to be modular forms. Modular forms, they're those special functions, deep connections to number theory and even string theory.
Exactly. Now, Zagier's conjecture, it added this whole other layer of intrigue to this problem. You see, he spotted this pattern in some, known modular Nahm sums, and he came up with this idea of duality. Basically, he said, if you've got a modular Nahm sum, right, associated with a triple ABC, then it's dual. You get that by transforming ABC into A sup 1 sup, A sup 1 sub B, ba sup 1 sup B2, R24C, and that should also be modular.
So it's like this duality suggesting there's a symmetry in how Nahm sums work.
Precisely. Deeper structure governing how they behave, right? Then, boom, Wang comes along with his paper, throws a wrench in the works, he finds counterexamples.
Wait, hold on. Before we jump into those counterexamples, I just want to be clear. You mentioned A sup 1 sup.
Right.
So does that mean this matrix A, it always has to be, invertible for this duality to work?
That's a sharp observation. Yeah, the conjecture, it kind of assumes that A is invertible. Otherwise, well, you can't even define the dual.
Okay, that makes sense. So how did Wang find these counterexamples? Did he, directly try to disprove the whole conjecture?
No. Different approach. He focused on constructing specific counterexamples. He started by examining these known modular Nahm sums, and he carefully calculated their duals, using that transformation we just talked about.
And what did he find?
Well, he found that in a few cases, those dual Nahm sums, they weren't modular. They broke the pattern, disproving Zagier's conjecture.
So this beautiful symmetry, it didn't hold up in all cases. How did he prove those dual sums weren't modular, though?
Well, it's a clever mix of techniques from Q-series and modular forms, intricate transformations, substitutions, some powerful identities. He really, he expressed those dual Nahm sums in a way that, clearly showed they weren't modular. Pretty elegant, actually.
Okay, before we get to the specifics of those counterexamples, there was a generalization of Zagier's conjecture that Wang also tackled in his paper, right?
Right. Mizuno's work. He proposed a generalization, introduced modular quadruples. These quadruples, they have a matrix A, a vector B, a scalar C, and this diagonal matrix D called a symmetrizer.
So it's like Zagier's conjecture, but with this extra layer of complexity.
Exactly. Mizuno, he conjectured a similar duality principle for these generalized Nahm sums. He stated that if you have a modular quadruple, A, B, C, D, then it's dual. You get it by transforming A, B, C, D into A sup 1 sup, A sup 1 sup PB, sup 1 80 sup P2, TRD 24C, D would also be modular.
Okay, so basically extending that duality idea to a wider class of Nahm sums. Did this generalized conjecture hold up any better?
Not really. Wang, he systematically checked Mizuno's examples, and just like with Zagier's conjecture, he found counterexamples. These duality principles, while they're kind of beautiful, didn't always hold true.
This is getting really interesting. Can we walk through one of those counterexamples from the paper?
Absolutely. Let's take Mizuno's fifth example. It involves a rank 3 matrix A, a symmetrizer D, and a set of vectors B. We'll start on page 5.
Okay, sounds good.
So he starts with this matrix. A, 2, 2, 2, 2, 4, 4, 4, 1, 2, 3.
3 by 3 matrix. What about the symmetrizer D?
The symmetrizer D, it's a diagonal matrix. D equals diag 2, 2, 1. So when you multiply A and D, you get a symmetric positive definite matrix. So when you multiply A and D, you get a symmetric positive definite matrix, AD. So when you multiply A and D, you get a symmetric positive definite matrix, 4, 4, 2. So when you multiply A and D, you get symmetric positive definite matrix, 4, 8, 4. So when you multiply A and D, you get a symmetric positive definite matrix, 2, 4, 3.
Got it. What about those vectors, B?
Mizuno, he gave 10 vectors B. Let's just focus on 3 specific ones. B0, 0, Nicus 1, B1, minus 1, B1 equals 1, 0, 12, B2 equals 3, 4, 52. Wang and his co-author, they already had some interesting results about these.
Interesting. What kind of results?
They proved that the generalized Nahm sum, the one associated with A, B0, minus 148D, it's modular, but the ones associated with A, B1CD and A, B2CD, they're not modular, no matter what C is.
So a mix of modular and non-modular ones. What does this tell us about Mizuno's conjecture?
Well, Mizuno's conjecture, it predicts that the duals of all these, they should, also have corresponding modularity. We need to calculate the duals.
All right, dual calculations time. What's the dual of A?
It's just its inverse. A is sup 1 sup, 1 negative 12, 0 negative 12, 1 negative 1, negative 0, negative 12, 1. And D, the symmetrizer, stays the same in the dual, and D, the symmetrizer, stays the same in the dual, AD, and D, the symmetrizer, stays the same in the dual, 0, negative 1, 0, negative 1, and D, the symmetrizer, stays the same in the dual, 0, negative 1, 1. And D, the symmetrizer, stays the same in the dual, 0, negative 1, 1.
Okay, and the duals of those vectors, B0, B1, and B2.
You apply that transformation, A sub 1 sub B, you get B0 managed to 1, 0, negative 12, B1 negative 1, 12, B2, which is 1, 0, 12. The duals of B1 and B2, they're the same.
Interesting. So now we have the dual quadruples. The big question, do their modularity properties line up with Mizuno's conjecture?
That's where it gets exciting. To answer that, we need to dive into these identities Wang found. 3 remarkable identities. Each one involves a triple sum. They're on pages 6 and 7.
Triple sums. Okay, lay down.
The first one, it involves that dual quadruple A, B0, C, I, D. It says the generalized Nahm sum is equal to for 1 plus Q sub 12 sub, Q sub 2 sub 6, Q sub 12 sub, Q sub 12 sub, Q sub 12 sub, that AQ sub, that's the standard q-hypergeometric symbol.
What's so special about that identity? Looks pretty complex.
The right-hand side, it tells us this generalized Nahm sum, it's not modular. Because of that, Q sub 12 sub factor, that's not a modular form.
So even though A, B0, 10848D gives a modular generalized Nahm sum, its dual doesn't. Contradicts Mizuno's conjecture.
Exactly. And it gets even more interesting. The second and third identities, they use that dual quadruple, A, B1, 18D, which is also the dual of A, B2, 18D.
Right, because B1 and B2 are the same. What do those identities show?
They show the generalized Nahm sum for A, B1, 18D, IS modular. Wang proves it's equal to 3 Q sub 2 sub Q sub 2 sub 3 sub, which is a modular form.
Hold on. The dual of A, B1, C, D, which isn't modular no matter what C is, becomes modular for a specific C.
Precisely. And same goes for A, B2, C, D. Another counterexample to Mizuno's conjecture. Duality, it doesn't always preserve modularity in a, straightforward way.
This is remarkable. 2 cases where the duality breaks down. Modular to non-modular and non-modular to modular.
Exactly. Big implications for how we understand duality and Nahm sums. It's more complex than we thought.
I'm really curious about how those identities are proven. Can we walk through one of them?
Sure. Let's look at the first identity, page 6. It has several steps, some clever manipulations.
Okay, I'm ready.
So first, he expresses that generalized Nahm sum associated with A, B0, C, D as a triple sum, using the definition. Then he does some transformations, changes variables, uses the q-binomial theorem.
The q-binomial theorem. Remind me what that is.
It's a conologue of the regular binomial theorem. Expresses a q-series as an infinite product. Powerful tool for manipulating these series.
Okay. So he simplifies the triple sum using that.
Yes. He reduces the triple sum to a double sum. The next step, he uses a special case of an identity by Andrews. He expresses the double sum in terms of a single sum.
And that single sum is easier to work with.
Much easier. Then, the final step, another identity, a special case of Watson's quantologue of Ripple's theorem. This one, he uses it to express that single sum in terms of a product of q-hypergeometric symbols. That's the right-hand side of the identity.
Wow, a lot of steps, each one using some pretty advanced Q-series stuff.
It shows how well Wang knows these techniques.
So to recap, he started with the generalized Nahm sum, went to a triple sum, simplified it to a double sum, then a single sum. Then finally, he used those powerful identities to show it as a product of q-hypergeometric symbols. And that final form, it showed the dual sum is not modular.
Exactly. Beautiful piece of work.
It's clear we're just scratching the surface here. There's so much more to explore in Wang's paper, the other identities, and what these findings mean for Nahm's problem.
Absolutely. A lot more to uncover. You know what's really interesting is how Wang connects these generalized Nahm sums to the original Nahm sums. It leads to even more counterexamples, this time to Zagier's original conjecture.
Okay, how did he do that? How do you go from those triple sums with the quadruples to the regular Nahm sums, the ones with just the matrix A, the vector B, and the scalar C?
He uses this clever identity. It expresses a single q factorial in terms of a double sum. It's like taking one ingredient and breaking it down into two components.
I like that analogy. So he uses this to turn those generalized Nahm sums with quadruples into regular Nahm sums with triples.
Exactly. And by carefully choosing the exponents in those triple sums, he can control the resulting matrix A and vector B in the Nahm sum.
So what happens when he applies this to those counterexamples to Mizuno's conjecture? Do we get counterexamples to Zagier's conjecture too?
Yeah, we do. Remember that modular generalized Nahm sum, the one associated with A, B, 0, next 148, D? Well, he applies this transformation and expresses it as a regular Nahm sum. It has a 4x4 matrix. A equals 1, 0, 0, minus 12, 0, 0, 1, manage to 12, manage to 12, manage to 12, manage to 12, 1. It's on page 9.
Okay, so a bigger matrix now. What about the vector B and the scalar C for this Nahm sum?
The vector B is B equals a vector due, the natural 14, 0, and the scalar C, it's 0.
So this Nahm sum with this specific A, B, and C, it's modular. What about its dual? Zagier's conjecture says that should be modular too, right?
That's what the conjecture says. But when Wang calculated the dual, using that A sup 1 sup, sup 1 sup, the 1 sup sub u, specific sup sum sub u to R24C transformation, it turned out to be not modular.
Wow, so he created a direct counterexample to Zagier's conjecture using that transformation.
Exactly. It's like a chain reaction. Counterexamples to Mizuno's conjecture leading to counterexamples to Zagier's.
I'm guessing there's more. What about those other generalized Nahm sums, the ones associated with B1 and B2?
Those lead to even more interesting things. Remember, those generalized Nahm sums, they were not modular no matter what C was. But when Wang applied the transformation and calculated the regular Nahm sums, something unexpected happened.
Okay, what happened?
He found that for a specific value of C, the Nahm sums associated with B1 and B2, they became modular.
So even though the generalized Nahm sums weren't modular, their transformed versions could be made modular. Fascinating. What are the specifics? The matrices, vectors, and that special C value.
For both B1 and B2, the transformation gave the same 4x4 matrix A. A equals 1, 0, 0, 0, 12, 0, 0, 1, negative 12, and negative 12, negative 12, negative 12, 1. Same one as before, actually.
Interesting. What about the B vectors and the C value?
For B1, the vector B is B equals 0, 12, 12, negative 12. And for B2, B equals 0, 12, 12, 0. And for B2, the C value that makes them modular, it's 116 for both.
So these Nahm sums are modular for C equals 116. But Zagier's conjecture, their duals shouldn't be modular, right?
You got it. And Wang's calculations, they confirm that. The duals in these cases, they're not modular. They end up being sums of two modular forms, but with different weights, so they can't be modular themselves.
This is amazing. So Wang found counterexamples, but he also found this, hidden modularity with his transformations. The transformation itself made them modular when they weren't before.
That's a great way to put it. It shows how complex the relationship is between Nahm sums and their duals.
All this talk about transformations and duals, it makes me think about the actual techniques Wang used. We've mentioned Q-series and modular forms, but what about the proofs themselves? What did he actually do?
Wang's proofs, they're master classes in Q-series manipulation. He uses generating functions, constant term extractors, some really clever substitutions.
So we see an example, maybe a quick walkthrough of a snippet of one of the proofs.
Sure. Let's look at how he proves one of those single-sum Rogers-Ramanujan type identities. Those are really important for the triple-sum identities we talked about earlier. It's on page 8.
Okay, go for it.
One of the identities is QK Hurier, QK2, 1 Dozier Diodoriu, 1 Dergio, Q2K, Q2K, Q2, Q2, Q22, Q2, Q222, Q2K, Q22, Q2, Q2 Fourier.
Whoa. That's a lot to take in.
It might look complicated, but the key is to see the structure. Those in Q2K and -1 Q2K terms, they tell us to use Bailey pairs.
Right, Bailey pairs. What were those again?
A Bailey pair, it's a pair of sequences with a specific relationship. They let you do powerful transformations with Q-series, like a decoder ring.
So they simplify things.
Exactly. Wang, he constructs a specific Bailey pair, and then he uses Bailey's lemma. That lemma, it's a tool for transforming Q-series identities.
Okay, so he uses Bailey's lemma with this Bailey pair, and he transforms that left-hand side into something simpler.
Exactly. Bailey's lemma, it lets him express that left-hand side as a combination of simpler Q-series. And then he manipulates those using other identities, like Jacobi's triple product identity.
And then eventually he gets that complex expression on the right-hand side.
Yes. He breaks down the complexity and reveals the structure. It's really quite elegant.
Sounds like it takes a lot of skill and patience to work with all that.
You're telling me. Wang's work, it's really remarkable.
Well, this has been an amazing journey so far. We've seen how Wang disproved both Zagier's and Mizuno's conjectures, found that hidden modularity, and even gotten a peek at the techniques he used. What a deep dive.
And we're not done yet. There's still more to explore. The implications of these findings and those foundational single-sum identities.
You're right. Always more to discover. Let's take a moment to, gather our thoughts, and then we'll continue our exploration in the last part of our deep dive.
Welcome back. Ready for more?
You bet. Last time we were talking about those techniques Wang used, those single-sum Rogers-Ramanujan identities. They were so simple, but so important to his work.
Yeah, they're pretty fascinating. They have a lot of significance in the world of Q-series, even though they might seem kind of obscure.
Can we dig into those a little more? Remind me what they look like again and why they're so crucial.
Sure. One of them is QK do 1 near 1, Q2K, Q2K, Q23, Q22, Q2, 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 Q22, Q2, Q4, Q4. We talked about Bailey pairs and Bailey's lemma, right? He uses those same techniques to prove these identities.
Right, those Bailey pairs. He uses them and Bailey's lemma to turn those single sums into expressions with infinite products, like those QQ subterms on the right-hand side.
Exactly. And those infinite products, they often tell us whether something's modular or not. It's really cool how Wang connected these single-sum identities to those more complex triple-sum generalized Nahm sums.
Yeah, like he found a hidden link between two seemingly separate areas of Q-series.
That's a good way to put it. And this connection, it gives us new ways to do research. We know these single-sum identities are important now, so we can look at them more closely, maybe see if they lead to even more discoveries about Nahm sums in modular form.
It's like he's given us a new toolkit, a new way to look at these problems, like a treasure map,
I like that. But speaking of new territory, we can't forget the big question. Zagier's and Mizuno's conjectures, they're disproven. So what does this mean for duality and Nahm sums?
Yeah, is duality just, gone? Or can we, fix it somehow?
That's where things get really exciting. Wang's counterexamples, they show the original conjectures. They're not always true. They don't mean duality is completely, useless.
So there's still, a chance for some kind of duality principle.
I think so. It's just that the relationship between Nahm sums and their duals, it's trickier than we thought. We need to, re-examine our assumptions, look for patterns in a new way.
So back to the drawing board, but with new knowledge and techniques because of Wang's work.
Exactly. We need to really look at these counterexamples, see when duality doesn't work, and explore, modifications or generalizations that might capture duality better.
Like we're detectives working on a puzzle. We have some clues, but we don't have the whole picture yet.
And who knows what else we'll find as we keep looking into this area. Maybe hidden symmetries, connections we haven't even thought of.
That's what makes math so cool, this constant search for knowledge and all the, twists and turns along the way.
Definitely. And sometimes when a conjecture is disproven, that's when we find the most interesting things.
Wang's work is a great example. He challenged what people believed, and now we have new areas to explore in math. Researchers are, rethinking how they approach Nahm sums.
It's true. As we wrap up our deep dive, I want you to think about this. What do Wang's findings mean for your own, mathematical work? What assumptions do you have that maybe you should look at again?
That's a great question for our listeners. Even in math, it's good to question things, explore, and, be ready for the unexpected.
So embrace the unknown, challenge what you think you know, and who knows, maybe you'll make the next big discovery that changes how we see math.
And that brings us to the end of our deep dive. Thanks for joining us, everyone, and keep exploring the world of math. Welcome to the Deep Dive. Today we're going to be diving deep into some pretty fascinating mathematics. We're looking at a paper called Counterexamples to Zagier's Duality Conjecture on Nahm sums. And, well, it looks like we're in for a real challenge.
Oh, absolutely. This paper really tackles a conjecture that's captivated mathematicians for years. It's Zagier's duality conjecture. It's this bold claim about a kind of symmetry in the world of Nahm sums. And this paper, well, claims to have found places where this symmetry breaks down.
Already hooked. So to set the stage for our deep dive, could you remind us, what are Nahm sums? Why are they so important?
Of course, Nahm sums, they're a special type of, well, infinite series. They pop up in a lot of areas of math, especially number theory and even physics sometimes. You can actually see their definition in equation 1.1 of the paper.
Okay, let me see. Equation 1.1.
Yeah.
I can see it. It's a little intimidating. Can you break it down for us a bit?
Sure. So we denote the Nahm sum as F subscript A, B, C of Q. A is a positive definite matrix, B is a vector, and then C is a scalar. Then we sum over all vectors and they have non-negative integer components. Q is a complex variable. And you'll notice the expression inside the sum, it involves the interplay of n with A, B, and C. The denominator, that's particularly interesting because it's a product of what we call q-Poch-Hammer symbols. Those are really fundamental building blocks in the theory of Q-series.
Okay, so it seems like there's a lot going on there.
Hey,
But the
Glenn.
main idea is we're dealing with an infinite series, and it involves these specific mathematical objects like matrices, vectors, scalars. So now, where does this concept of modularity come in?
Ah, yes. Modularity. It's absolutely crucial in number theory. It's like a symmetry, but on a much deeper level than, say, the symmetries we see in everyday objects. A modular function, it behaves a certain way under certain transformations. Basically, if you apply a specific transformation to the input, the output will change in a predictable and structured way.
So it's like there's a hidden pattern or a code within the function.
Exactly. And when a Nahm sum is modular, it hints at this much deeper structure. And it even suggests connections to other areas of mathematics.
Okay, I'm starting to see why this modularity is such a big deal.
Yeah.
Now let's talk about Zagier's conjecture. What was his bold claim about Nahm sums?
Well, Zagier observed this fascinating phenomenon in certain modular Nahm sums, a kind of duality. He suggested that if you take a modular Nahm sum and apply a special transformation to its parts, the matrix A, the vector B, the scalar C, you get another function. And, get this, it's also modular. It's like a mirror image in the world of Nahm sums, where modularity is preserved.
That's a pretty elegant idea. So he's saying there's this hidden symmetry, this duality, specifically within modular Nahm sum.
Exactly.
Yep.
And his conjecture, which is laid out in conjecture 1.1 of the paper, it gives a specific formula for this duality transformation. You can see it in equation 1.4. He proposes that if you start with what we call a modular triple, that's the A, B, and C, and you apply this transformation, you'll get another modular triple.
So if you've got a Nahm sum, and it's in this modular club, you can apply Zagier's transformation, and the result, it'll still be in the club.
Right? That's the heart of his conjecture. And, he had good evidence for it, too. For instance, the conditions for Nahm sums to be modular, well, they seem to be invariant under this transformation.
So the rules for being in the modular club, they don't seem to change after applying Zagier's transformation.
Exactly. There was also evidence from how these Nahm sums behave as the input gets really large. We call this the asymptotic behavior. The original and the transformed, well, they seem to align, which further supported the idea of this duality.
Okay, so there was this, I guess you could say, harmony in the math that was supporting Zagier's conjecture. But then, now we have this paper. It claims to have found counterexamples. So where did these counterexamples come from?
Well, it gets a little more complicated when we introduce the concept of generalized Nahm sums. You can see this in equation 1.5. These are like Nahm sums, but with an extra layer of, complexity. They have an additional diagonal matrix, we'll call it D, with positive integer entries.
So we're taking the original Nahm sum and tweaking it a bit with this D matrix.
Exactly. And this D matrix acts as a kind of symmetrizer. It influences the behavior of the Nahm sum, but in subtle ways. Mizuno, building on Zagier's work, proposed a very similar duality conjecture, but for these generalized Nahm sums. You can see this in conjecture 1.2.
So Mizuno took Zagier's idea of duality and basically expanded it to include this broader class of Nahm sums.
Yes. And his proposed transformation for these generalized Nahm sums, that's given in equation 1.6. But as Mizuno dug deeper, he started finding, cracks in this seemingly perfect duality picture. He was focusing on what we call rank 3 examples, meaning the matrix A in these generalized Nahm sums. It was a 3x3 matrix.
So things get interesting when we move to these more complex rank 3 generalized Nahm sums.
Precisely.
Yeah.
Mizuno found some specific combinations of A, B, C, and D where the duality conjecture just didn't hold up. For example, he found a case where the original generalized Nahm sum was definitely modular. You can see that in equation 1.8. But its dual, the one you get after using Mizuno's transformation, well, it was demonstrably not modular.
So in this case, the mirror image, it didn't inherit the modularity.
Exactly. And this wasn't just a one-time thing. Mizuno found multiple examples where this duality just, well, failed.
Wow. Okay, this is where it really starts to get interesting. We've got these counterexamples that challenge this whole idea of duality in Nahm sums. So where do we go from here? What does the paper do with these findings?
Oh, the paper really dives deep into analyzing these counterexamples. It tries to understand why this duality breaks down. And to do that, we have to get into some pretty sophisticated mathematical tools.
Well, this is getting even more exciting. I can't wait to explore the math behind these findings. Let's continue our deep dive in part 2.
Sounds great.
All right, so we're back, and we're ready to really dig into these counterexamples that challenge those duality conjectures. Last time, we ended with Mizuno finding those specific cases where duality seemed to break down. So what's next in our mathematical detective story?
Well, the next step is to take a closer look at those counterexamples, right? The paper focuses on what we call the dual quadruples associated with the cases where Mizuno's conjecture didn't work out. You can see those listed in equation 1.11.
Okay, so just so we're clear, these dual quadruples, they represent the transformed versions of the original parameters, the A, B, C, and D. We're basically looking at what happens after applying Mizuno's transformation, right?
Exactly. Remember, the whole idea behind these duality conjectures was if you start with a modular Nahm sum and then you apply this transformation, you should end up with another one that's also modular. But, well, Mizuno found places where that just didn't happen.
Right. The mirror image didn't, reflect the modularity.
Yeah.
So how do these dual quadruples, these equation 1.11 ones, how do they help us understand what's going on?
Well, the paper uses those dual quadruples to establish some pretty crucial identities. Those are laid out in theorem 1.3. Take a look at equations 1.12, 1.13, and 1.14. Each of those, it involves a Nahm sum that's constructed using one of those dual quadruples from, equation 1.11.
Okay, I see. Each equation kind of expresses the dual Nahm sum, the one we get after the transformation. It expresses it in a very specific form. But how do these equations actually reveal the breakdown of the duality? I'm not quite seeing it yet.
Okay, so the key is in the types of functions on the right-hand side of those equations. For instance, equation 1.12, it shows that the dual Nahm sum that comes from that first dual quadruple is not a modular function. And this is, even though the one before the transformation, it was proven to be modular, it directly contradicts Mizuno's conjecture.
So the original, it was in the modular club, but it's dual. After the transformation, it got kicked out.
Exactly. And it gets even weirder, actually. Equations 1.13 and 1.14, they show that the dual Nahm sums that come from the second and third dual quadruples, well, those are modular. But here's the catch. The original generalized Nahm sums in those cases, they were not modular to begin with.
Hold on. So the reflection is like more modular than the original image. That seems backwards.
It's definitely counterintuitive. These findings really show that the relationship between a generalized Nahm sum and its dual is much more subtle than we originally thought. It's not just a simple reflection where modularity is always preserved.
Yeah, this is where my brain starts to hurt. So how does the paper actually explain these, paradoxical results? How do we make sense of this duality breakdown?
To really get it, we need to look at the proofs. And fair warning, this is where things get a bit technical. The paper uses this powerful tool from the theory of Q-series, and it's called Bailey pairs.
Okay, Bailey pairs. Got it. But to be honest, I'm not really sure what those are. Can you give us a quick explanation before we dive into the math weeds?
Sure. Think of Bailey pairs as a pair of sequences. They have to satisfy a very specific relationship. They're kind of like building blocks for creating and manipulating more complex Q-series. And, well, that includes Nahm sums.
So they're like special ingredients that mathematicians use to cook up these intricate Q-series formulas.
Perfect analogy. And the paper introduces 4 new Bailey pairs, which are defined in Lemma 2.1. They're essential for proving the identities in Theorem 1.3.
So these Bailey pairs are like secret weapons for unraveling these complex relationships.
You got it. The proofs involve this technique called Bailey's lemma, which allows you to transform one Bailey pair into another one. By choosing these Bailey pairs very carefully and manipulating them just right, the authors get those identities in Theorem 1.3, and ultimately those show that Mizuno's conjecture doesn't always work.
Okay, I think I'm following so far. So we've got these counterexamples to Mizuno's conjecture, and Bailey pairs are kind of the stars of the show in the proofs. Is there anything else that the paper looks at related to these findings?
Yeah, it also gets into something called single-sum Rogers-Ramanujan type identities. These are a special class of Q-series identities, and they're connected to the well-known Rogers-Ramanujan identities.
Oh, yeah, the Rogers-Ramanujan identities.
Yeah.
They're some of the most beautiful formulas in math, right?
Absolutely. They're classic examples of modular Q-series identities. And these single-sum ones, they're kind of like their I guess you could say simpler cousins, but they're still pretty remarkable, and they actually play a crucial role in understanding those counterexamples to the duality conjecture.
So these single-sum identities give us more insight into why the duality doesn't always work.
Precisely. The paper presents 4 of these single-sum identities in Theorem 1.4, specifically equations 1.15, 1.16, 1.17, 1.18. They're like extra pieces of the puzzle, giving us more information about how these Nahm sums and their duals behave.
It's amazing how all these different parts of math come together to shed light on this problem. It's like we're using Bailey pairs and Rogers-Ramanujan type identities and all sorts of other things to try to solve this duality mystery.
It really shows how interconnected math is. Different concepts and techniques from different areas, well, they can come together to solve a problem, sometimes in unexpected ways.
All right, so we've seen how the paper uses Bailey pairs and these single-sum Rogers-Ramanujan type identities to really analyze the counterexamples to Mizuno's conjecture. But remember, Mizuno's conjecture, that was an extension of Zagier's original one for, regular Nahm sums. Does the paper say anything about Zagier's conjecture, considering these new findings?
You're right. We can't forget about Zagier's original conjecture. And it turns out these counterexamples to Mizuno's conjecture, well, they have implications for Zagier's too.
Ooh, okay, now this is getting really interesting. So what's the verdict? What happens to Zagier's conjecture?
Well, it doesn't look good for Zagier's conjecture, unfortunately. These counterexamples, they're a big problem for it. Theorem 1.5 in the paper, it presents specific Nahm sums, and remember, these are regular Nahm sums, not the generalized ones that are definitely modular. You can see those in equation 1.1. But when you apply Zagier's transformation, the duals you get, well, they're not modular. Those are in equation 1.20.
So even Zagier's original idea about the duality of just regular Nahm sums, that doesn't always hold up either. It seems like this whole duality thing is falling apart.
Well, I wouldn't say falling apart, but we definitely need a more nuanced understanding of it. It's important to remember that even though these counterexamples disprove those conjectures, Zagier's and Mizuno's, in their, absolute forms, they don't invalidate the whole concept of duality. What they do is highlight the need for a more sophisticated approach to studying it.
So instead of throwing out duality altogether, we need to figure out when and how it actually works and when it doesn't.
Exactly. These counterexamples, they're like signposts. They point us towards a more, well, intricate and maybe even more fascinating mathematical landscape. They're not failures, really, but more like opportunities to explore things more deeply.
I love that perspective. I'm really curious to see where this all leads. What other avenues does the paper explore, given these new findings?
Well, in part 3, we'll move beyond these specific counterexamples. We'll look at the bigger picture. What do these findings mean for, for how we think about duality in Nahm sums? What new questions do they raise? And, what are the potential implications for other areas of math, maybe even physics?
I can't wait to unpack all of that. Let's take a short break, and then we'll dive into that final part of our deep dive. All right, we're at the final part of our deep dive into this world of Nahm sums and duality. And, we've seen how those conjectures, Zagier's and Mizuno's, well, they were elegant, but ultimately challenged by those counterexamples. So where do we go from here? What does it all mean?
Well, those counterexamples, they don't just disprove specific conjectures. They make us rethink duality and Nahm sums more generally. And honestly, we're left with, more questions than answers. But that's exciting, right? It's how math moves forward.
I get that. It is exciting. But I have to admit, I'm a little bummed those beautiful conjectures didn't hold up. But I am really intrigued by these new mysteries. What are, the big questions mathematicians are working on now?
Well, one of the most basic ones is under what conditions does duality actually work for Nahm sums? We know it's not universal, but maybe there are like special types of Nahm sums or maybe certain limits on the matrices and vectors we use where duality actually is preserved.
So it's like we're mapping out this modular mirror world, but we got to figure out where the reflections are, accurate and where they get all distorted.
Exactly. It's all about this balance between the structure of the Nahm sum and the properties of its dual. Another really interesting question has to do with those single sum Rogers-Ramanujan type identities.
Oh, you mean those, like, simpler cousins of the Rogers-Ramanujan identities? The ones that give us clues about, the duality breaking down?
Yeah, exactly. The paper only showed like 4 of those identities, but who knows how many more are out there. If we could find and prove more of them, we might see deeper patterns, maybe even a way to like fully understand this whole duality thing.
Like finding more pieces of a giant puzzle. Each identity adds a little bit more to the picture. It's also cool to think about what these counterexamples might mean for, you know, other parts of math. I'm especially curious about physics, like conformal field theory.
Oh, yeah, that's a fascinating area where these findings could have a real impact. Remember how modularity in Nahm sums is connected to symmetries and dualities in conformal field theory? Well, if the duality we expected in Nahm sums isn't always there, it makes us wonder about those physical theories too.
So could these math discoveries guide physicists as they try to find new laws of the universe? It's amazing to think about.
It just goes to show you how connected math and physics are. Abstract math ideas can have huge implications for how we understand the physical world. And it goes both ways. What physicists observe can give mathematicians new ideas to explore.
I'm honestly in awe of how deep and complex this part of math is. It's incredible how these, I guess you could say, esoteric concepts can have such far-reaching consequences. So for our listeners who might be, feeling a bit overwhelmed by all this, what would you say is the main takeaway from our deep dive?
I think the biggest thing to remember is that math is always changing. It's not about just, memorizing formulas or blindly accepting what's already known. It's about asking questions, challenging what we think we know, and pushing the boundaries of our understanding.
It's about embracing the mystery and the excitement of discovery. Even though these counterexamples shook things up a bit, they've given us new things to explore. They've shown that, even when conjectures are proven wrong, it can lead to a much deeper and richer understanding of the ideas behind them.
Couldn't have said it better myself. That's what makes math so captivating. It's a journey of exploration, and there are always unexpected twists and turns along the way. And often it leads to profound insights into the very nature of reality.
Well said. And to everyone listening, if you ever encounter a counterexample in your own life, don't get discouraged. It might just be the key to unlocking a whole new world of possibilities. Until next time, keep exploring, keep questioning, and keep diving deep into the amazing world of mathematics. Welcome to another deep dive, and let me tell you, we're going to get into some really fascinating math today. We're going to be exploring a paper that actually challenges a long-held assumption in the world of something called Nahm sums. So if you're ready to kind of unravel some of these mysteries of mathematics, well, buckle up.
Yeah. It's really amazing how this paper kind of brings together these seemingly different parts of mathematics. We've got things like Q-series and modular forms, and they come together through these objects called Nahm sums.
Okay, I'm already intrigued. But just so everyone's on the same page, can you kind of remind us about these Q-series and modular forms? I mean, what makes them so special in math?
Oh, absolutely. So think of a Q series kind of like an infinite sum. And in this sum, you've got, powers of this variable Q. And often these powers create these really cool patterns. And the thing is, they show up everywhere in mathematics. Like you'll find them in number theory, combinatorics, all sorts of places. Now, on the other hand, modular forms are these functions that have this amazing symmetry. It's like no matter how you transform their inputs, in certain specific ways, they stay basically the same. Kind of like, you see a kaleidoscope and you rotate it, but the pattern still looks beautiful.
Okay, so it's like you're finding this hidden order, this hidden symmetry
Yeah.
within these infinite numbers.
Exactly. You got it. Now, when you talk about Nahm's problem, what you're really asking is, when do these Nahm sums, which remember are built using these Q-series, when do they actually show this property of modularity? And finding modularity, in a Nahm sum, it's almost like you're discovering a blueprint, It reveals this deeper structure within the Nahm sum.
Oh, I get it. So it's like we're trying to find this secret code that kind of unlocks what these mathematical objects are all about.
You got it. Exactly. And this is where this paper we're diving into comes in. It's called Counterexamples to Zagier's Duality Conjecture on Nahm sums. It's written by Liuquan Wang. And what's really wild is it shows us that a very old idea called Zagier's Duality Conjecture about this whole modularity of Nahm sums, well, it's not always true.
Whoa, hold on, that's a twist. Okay, so let's jump right into this paper and see how it unravels this whole mystery.
Sounds good. So right off the bat, the paper kind of lays the foundation. It gives us equation 1.1, which defines what a Nahm sum actually is. And you'll notice that you have a matrix called A, you have a vector called B, and then you have a scalar, which is just a regular number called C. And of course, you see those q-hypergeometric symbols down there in the denominator.
Oh yeah, those q-hypergeometric symbols. I kind of remember them from, way back when, but maybe just a quick refresher on what they actually do in these Nahm sums.
Of course. Think of the q-hypergeometric symbol, which you can find in equation 1.2, as kind of like a building block for creating these more complicated q-series. What it does is it makes sure that the infinite sum in the Nahm sum actually converges nicely. So it's not going to just fly off to infinity. It's like, imagine adding a little bit of, a pinch of salt to a recipe, just to bring out the flavors.
This is like making the Nahm sum a little tastier for mathematicians, right?
Exactly. Now, to give you a really clear picture of what a modular Nahm sum looks like, the paper gives us a really famous example, the Rogers-Ramanujan identities. You can see those in equation 1.3. These identities, they've been a puzzle for mathematicians for over a century. They perfectly show how a Nahm sum, even one with a simple, rank 1 matrix, A can actually be modular.
The Rogers-Ramanujan identities, those are like math superstars. They always pop up in the coolest places.
They sure do. And they show us how elegant this whole idea of a Nahm sum being modular can be. Now, building on this, the paper introduces us to Zagier's duality conjecture. That's conjecture 1.1.
Okay, let's break down this conjecture a bit. What's Zagier actually saying about these Nahm sums?
Well, he's basically proposing that if you've got a modular Nahm sum, you can kind of make a mirror image of it, a dual, by doing a few things. You got to invert the matrix A, and then make a couple of adjustments to the vector B and that scalar C. And what he conjectured was this dual Nahm sum, it should also be modular.
So it's like if one side of the Nahm sum shows this modularity, then its reflection, its mirror image, should too.
Exactly. And you can see exactly how to make this dual in equation 1.4. It's like a recipe for creating a mirror image. Now, at first, there was a lot of evidence that made everyone think, hey, this conjecture is probably right. But this paper we're looking at, it found some hidden counterexamples, like there were some things lurking beneath the surface that nobody had noticed before.
Oh, this is getting interesting. But before we move on, I just want to make sure I'm really grasping this whole duality thing. What's so important about inverting that matrix A in this whole concept?
Great question. So think of the matrix A as like the shape, the structure of the Nahm sum. Inverting it is kind of like making an inverse shape, a mirror image in the world of matrices. And this inversion, together with those little tweaks to the vector B and the scalar C, it creates a brand new Nahm sum. And what Zagier thought was this new sum, it should keep that special property of modularity.
I see. So you're kind of flipping the Nahm sum over, but you're doing it in this very precise way that's supposed to keep its symmetrical beauty intact.
Yeah.
But you said there were these counterexamples. Where does the paper go from there?
Right. So the paper then talks about the work of another mathematician, Mizuno. He took Zagier's ideas and made them even, more general. He introduced these things called generalized Nahm sums, and you can see the definition in equation 1.5. These new sums add another layer of complexity because now you've got a new diagonal matrix D in the mix.
Okay, so Mizuno kind of added a whole new dimension to the problem. What's the role of this new matrix D in these fancy generalized Nahm sums?
The key here is that for Mizuno's generalized Nahm sums to work, the matrix A has to be what we call symmetrizable, and this is where matrix D comes in. So when you multiply A by D, you get a matrix that's symmetric and also positive definite. These properties make sure the generalized Nahm sums behave nicely.
So matrix D is like the symmetrizer, right? It keeps everything in order. Did Mizuno also make a conjecture about duality for these generalized Nahm sums?
He did, actually. He followed Zagier's lead and came up with his own duality conjecture for these generalized sums. It's conjecture 1.2 in the paper. And he found some evidence that supported his idea, at least for matrices with a rank of 2. But then he and Wang came across some examples with a rank of 3 that didn't fit the pattern at all.
So that's where the trouble starts brewing. These rank 3 examples must be holding some key to this whole mystery, right?
Absolutely. And that's where the paper dives deeper, starting with equation 1.7. This introduces a specific matrix A and its symmetrizer D. But the real drama begins with 3 vectors, B0, B1, and B2.
So these vectors are like the main characters in our mathematical play. How do they challenge these duality conjectures?
All right, so take a look at equations 1.8, 1.9, and 1.0. They show something really interesting. The generalized Nahm sum made with the vector B0. It's modular, just like Mizuno's conjecture predicted. But then you look at the sums made with vectors B1 and B2, and they just refuse to be modular. No matter what value you pick for that scalar C, they just won't cooperate.
Hold on, so one vector works, but the others don't. That goes directly against Mizuno's conjecture. This is getting more exciting by the minute.
I know, right? And these non-modular examples become crucial clues. The paper uses them to build these special things called dual quadruples. You can see those in equation 1.21. They're like mathematical fingerprints pointing towards potential problems with Zagier's original conjecture.
So it's like the paper is building a case step by step against these conjectures. What happens next?
Well, the first major breakthrough comes in the form of theorem 1.3. This theorem gives us 3 identities. Those are equations 1.12, 1.13, and 1.13. And these, let me tell you, they deliver a decisive blow to Mizuno's conjecture.
Okay, hold up a sec. Let's take a closer look at these identities. What exactly are they telling us about Mizuno's conjecture?
All right, so each of these identities shows us a case where you've got this perfectly fine modular generalized Nahm sum, but then you create its dual, following Mizuno's instructions, and boom, it's not modular. It's like finding a crack in a mirror, like the reflection isn't quite right.
Wow, so Mizuno's conjecture is definitely in trouble. But what about Zagier's original conjecture? Does it survive these attacks? I'm dying to know.
Well, the paper doesn't stop there. It takes these counterexamples against Mizuno and uses them to target Zagier's conjecture directly. And let me tell you, the result is quite dramatic.
Oh, I bet. You gotta tell me, does Zagier's conjecture escape unscathed?
It does not. But I think we need a little break before we unveil the grand finale and reveal how Zagier's conjecture ultimately meets its demise. It most certainly does not. But the clever part is the paper doesn't just find counterexamples. It actually helps us understand how the 2 conjectures, Mizuno's and Zagier's, are connected. And it's not like a simple connection, like one thing causing another. It's much more subtle than that.
That's fascinating. So even though both of these conjectures end up being wrong, the connection between them is more complicated than we first thought.
Exactly. To really appreciate how elegant Wang's argument is, we have to look at the proof of theorem 1.4. It's kind of the foundation of the whole paper. You can find it in section 2, preliminaries. This is where we get all the tools and techniques we need for the big job ahead.
Okay, so let's get our hands dirty and dive into these preliminaries, huh? What kind of mathematical gadgets does this paper give us to work with?
Well, first, it reminds us of some really important Q-series identities. You've got equation 2.1, which is Euler's exponential identity. It's a classic. It takes this infinite sum and writes it in a super compact form. Then there's equation 2.2, which is like a variation on that same theme.
Yeah.
It adds a little twist to the exponent of the Q. These identities are like essential tools for any mathematician working with Q-series.
Ah, Euler's exponential identity. I remember that one. It's like you take this never-ending sum and poof, you've got a neat and tidy little expression. But what about some of the other tools?
Right. So then the paper introduces us to Ramanujan's theta functions. You can find those in equations 2.3 and 2.4. These functions, they're like rock stars in the world of math. They're famous for their symmetry and their connection to number theory. And they're really important here because they help us connect Q-series to modular forms. We can take these complicated sums and express them using these beautifully symmetric functions.
Oh yeah, Ramanujan's theta functions, those are always a pleasure to see. They have this like mysterious aura about them,
For sure. And to give us even more firepower, the paper brings in Jacobi's identity. That's in equation 2.6. It's another really powerful tool for working with Q-series. It connects an infinite product to an infinite sum, which gives us another way to manipulate these expressions.
So we've got Euler, Ramanujan, and Jacobi all helping us out in this proof. That's a pretty impressive lineup.
Absolutely. The paper is using the best of the best here. Then it introduces the Q-Gauss summation formula. That's equation 2.7. This is a really strong formula that lets us sum up a particular type of Q-series in a closed form.
Ooh, the q-gas summation formula. I remember wrestling with that one back in grad school. It's a workhorse for sure, but it can be a little tricky to handle.
Yeah, you got to be careful with it.
Huh.
But it's essential for simplifying those really complicated Q-series expressions. Now, to dig deeper into this proof, we need to talk about Bailey pairs.
Bailey pairs. Okay, that rings a bell, but I can't quite remember why they're so important. Can you refresh my memory?
Of course. A Bailey pair, it's basically two sequences that have a special relationship. You can see the definition in equation 2.8. They involve those Q-Pochhammer symbols again. Think of a Bailey pair as a dynamic duo in the world of Q-series. They work together to unlock all these hidden identities. And then there's Bailey's lemma, which gives us these amazing transformation formulas for these pairs, like in equations 2.9 and 2.0.
Oh, Bailey's lemma. It's like a transformer for Bailey pairs, right? It helps us switch between different forms and see those hidden connections.
Exactly. Bailey's lemma is what drives this whole proof forward. It helps us connect different Bailey pairs and ultimately show the hidden modularity of certain Nahm sums. And to give us even more tools, the paper introduces 4 brand new Bailey pairs in lemma 2.1, equations 2.11 through 2.14. These are like custom-made tools just for this proof.
So the author's like, all right, we need some specialized equipment for this job. Pretty cool what happens once we've got all these tools ready.
Then the paper sets its sights on proving theorem 1.4. This theorem gives us 4 single-sum Rogers-Ramanujan type identities. Equations 1.15 through 1.18 are the stars of the show here. They show us just how powerful Bailey pairs and Bailey's lemma can be for discovering these elegant, surprising identities.
So theorem 1.4 is like a stepping stone. It's an important result that helps us get to those counterexamples and disprove the duality conjectures.
You got it. These identities are crucial because we're going to use them later on to turn generalized Nahm sums into regular Nahm sums. That's how we connect Mizuno's world to Zagier's world. Okay, so then the paper moves on to section 3, proofs of the theorems. This is where the real action begins.
All right, let's get to the heart of the matter. Let's see how these conjectures get taken down. Where do we begin?
Well, the first target is theorem 1.3. That's the one that delivers the first blow to Mizuno's conjecture. To do this, the paper introduces a clever function, FU-V-W. You can see it in equation 3.3. It's a triple sum, which means it's got 3 variables, u, v, and w. These extra variables give us more flexibility to manipulate the expressions.
So it's like adding more dimensions to the problem so we can move around more easily.
Exactly. And then, using equation 2.2, the paper cleverly sums over 2 of the variables, I and j, in that f function. That gives us a simpler expression, which you can see in equation 3.4. This simplification is strategic. It makes the expressions much easier to work with.
So it's like strategically getting rid of some clutter to make the problem clear.
Exactly. Now, the proof of theorem 1.3 has 3 parts, and each part deals with one of the identities in equations 1.1, 1.13, and 1.15. In part 1, the paper goes after equation 1.1 by setting those variables u, v, and w in the function f to specific values. That gives us equation 3.5.
So it's like fine-tuning the settings on a machine to get a specific output, right?
Perfect analogy. Then the paper splits the sum in equation 3.5 into 2 parts, S0q and S1q. S0q is the sum over all the even values of k, and S1q is the sum over the odd values. This separation lets us analyze the expression more carefully.
Divide and conquer. By looking at the even and odd parts separately, the proof becomes a little easier to manage. What happens next?
Well, the paper very carefully evaluates S0q and S1q. It uses equation 2.7, that Q-Gauss summation formula we talked about, to write them in terms of infinite products. Those are in equations 3.6 and 3.7. This step is really important because infinite products are often easier to manipulate and connect to modular forms.
Ah, I see. It's like taking a complicated puzzle and turning it into a simpler one, where the pieces fit together more easily.
Exactly. And then, by taking those simplified expressions for S0q and S1q and plugging them back into equation 3.5, the proof gives us the identity in equation 1.1. Boom, first strike against Mizuno's conjecture.
Nice. One piece of the puzzle falls into place. What about the other 2 identities?
Okay, so for equation 1.13, the paper uses a similar strategy. It sets the variables in FUVW to get equation 3.8 and splits the sum into even and odd parts, S0q and S1q again, but this time it uses those single-sum Rogers-Ramanujan type identities from Theorem 1.4, specifically equations 1.15 and 1.17, to simplify S0q and S1q. You can see the results in equations 3.9 and 3.0.
So those identities from Theorem 1.4 are finally coming into play. It's all starting to connect.
You got it. And by substituting those simplified expressions back into equation 3.8, the proof arrives at the identity in equation 1.13, another strike against Mizuno's conjecture.
2 down, 1 to go. This strategy seems to be working pretty well. What about the last identity?
For equation 1.14, the paper follows a very similar pattern. It sets the variables in FU, VW to get equation 3.11 and splits the sum into even and odd parts, but this time we call them T0 and T1q. Once again, it uses those Rogers-Ramanujan type identities from Theorem 1.4, this time equations 1.16 and 1.18, to simplify T0q and T1q as shown in equations 3.12 and 3.13.
It's amazing how the paper brings all these different identities together to create this elegant proof. It's like watching a master weaver at work.
I know, right? It really showcases the power of mathematical reasoning. So by plugging those simplified expressions back into equation 3.11, we get the final identity equation, 1.14. And that, my friend, is the end of Mizuno's conjecture. Theorem 1.3 is proven.
Wow, that's pretty impressive. Mizuno's conjecture is officially down for the count. Now, I'm really excited to see how the paper tackles Zagier's conjecture. What's the plan of attack?
Well, the paper connects those generalized Nahm sums, where we found the counterexamples, to regular Nahm sums. That's the key to showing that the problems in Mizuno's world also exist in Zagier's world.
So it's like building a bridge between the two, showing that the cracks in one world extend to the other.
Precisely. The paper does this by first giving us equation 3.14. It's a really useful identity that expresses a q-Poch-hammer symbol as a sum of terms that have squares in the exponents of q.
Oh, I see. It's like a clever little trick.
It is, and it's going to play a key role in rewriting that function f in a way that connects generalized Nahm sums to regular Nahm sums. Equation 3.15 shows us exactly how this transformation works. It expresses f as a regular Nahm sum, which we call FAB0Q2. The matrix A stays the same, but the vector B changes a bit to include the parameters from f.
So it's like rearranging the pieces of a puzzle to create a new picture, but it's still related to the original one. But how do we know if this new picture is modular?
Great question. That's where the Dedekind eta function comes in. It's denoted as E2 in the paper. This function, which is defined in terms of Q, is a modular form of weight 12. That means it transforms in a specific way when we change its input. It's a fundamental tool in the theory of modular forms, and it's our way of checking for modularity.
Ah, the Dedekind eta function. So if we can express something using this function, we know it's a modular form, right? It's like the key to the modular club.
Exactly. So with this knowledge and that connection between generalized and regular Nahm sums, the paper sets out to prove Theorem 1.5, the final blow to Zagier's conjecture.
Okay, this is it, the moment of truth. How does the paper deliver the knockout punch?
By carefully selecting the parameters in F, the paper creates specific examples that show the problem with Zagier's conjecture. Equations 3.16 are the first step. By setting the parameters just right, the paper shows that FA B1018Q2 and FAB218Q2 can be written using the Dedekind eta function. That means they're modular.
So these are our good guys, the modular regular Nahm sums made from those generalized Nahm sums that weren't modular.
You got it. They have their modularity cards for sure. But here's the twist. The paper then looks at the duals of these well-behaved Nahm sums. It uses the same techniques to rewrite the generalized Nahm sums from equations 1.9 and 1.10 as regular Nahm sums, which you can see in equation 3.17. This gives us the dual Nahm sums, which we call FAB0Q2.
Ah, so now we're looking in the mirror at the reflections of these modular Nahm sums. Is this where Zagier's conjecture starts to fall apart?
You bet. Equations 3.19 and 3.20 reveal the fatal flaw. They show that these dual Nahm sums, FAB1CQ2 and FAB2CQ2, can't be expressed just using the Dedekind eta function. They need a mix of modular forms with different rates, which means they can't be modular themselves.
So these are our bad guys, the duals that break all the rules.
Exactly. These equations are the proof. They show that Zagier's conjecture, even though it was a beautiful idea, just doesn't hold up in every case. We've seen two conjectures fall apart right in front of us.
This is incredible. It shows how important it is to keep questioning and exploring in mathematics. Even the most established ideas can be overturned. But the paper doesn't just stop there, does it? It also tries to explain why finding counterexamples to Mizuno's conjecture doesn't always mean we'll find counterexamples for Zagier's conjecture.
You're right. The connection between the two isn't as straightforward as we might think. There's more to it than that. Yeah, you're absolutely right. There's more to the story. It's like just when you think you've got it figured out, there's another layer of complexity, right?
Totally. So how does the paper try to make sense of this strange relationship between these two conjectures?
Okay, so remember section 4, the concluding remarks. That's where the paper really shines a light on this weird connection. It gives us this specific example that shows sometimes, even when the dual of a generalized Nahm sum isn't modular, the dual of the regular Nahm sum that comes from it can still be modular.
Whoa, hold on. Exceptions to the exceptions. It's getting kind of wild. So even though both conjectures are wrong, the connection between them is way more intricate than we initially thought.
Exactly. And that's what makes this whole paper so groundbreaking. It's not just about proving or disproving things. It's about revealing these deep connections and subtle relationships within this, this incredible world of Nahm sums and modular forms. It's like every time we think we've got it all figured out, math throws us a curveball.
That's what I love about it. There's always something new to discover, always another layer to uncover. So what's the takeaway from all of this? I mean, where do we go from here?
Well, I think this paper does more than just debunk a couple of conjectures. It really opens up a whole new direction for research. I mean, think about it. We've got these generalized Nahm sums and regular Nahm sums, and their connection to modularity is way more complicated than anyone expected. There are so many questions to explore now.
That's exciting. It's like this paper didn't just close a door, it opened up a whole bunch of new ones. And that, my friends, is what makes mathematics so endlessly fascinating.
Couldn't have said it better myself.
So, to everyone listening, thanks for joining us on this deep dive into the world of advanced mathematics. We hope you've enjoyed the ride. And remember, keep exploring, keep questioning, and keep pushing the boundaries of what we know.
Yeah.
Until next time. Welcome back to the Deep Dive. Today we're taking a deep dive into a fascinating paper that's making waves in the world of mathematics. Counterexamples to Zagier's Duality Conjecture on Nahm sums.
Yes, this paper really digs into some intriguing questions about modularity and challenges, some long-held assumptions in the process.
Okay, I'm already curious. But before we jump into the counterexamples themselves, let's set the stage. What exactly are Nahm sums, and why should mathematicians care about them?
Well, think of Nahm sums as a special type of Q-series. They're mathematical expressions that involve powers of a variable Q combined in very specific ways. And they pop up in various areas, like number theory and even physics.
Well, they're kind of like mathematical building blocks with connections to different areas of math.
Exactly. And one of the key properties we look for in these Nahm sums is something called modularity.
Modularity. That sounds familiar. I vaguely remember it from my university days. But could you give us a refresher?
Of course. Modularity essentially refers to a kind of symmetry or pattern within the Nahm sum. When a Nahm sum is modular, it means it exhibits a hidden structure that links it to a special family of functions called modular forms.
And modular forms are a big deal, right? They have connections to various areas of mathematics.
Absolutely. They're like mathematical chameleons, appearing in fields like number theory, geometry, and even string theory. They possess remarkable properties and play a crucial role in understanding various mathematical structures.
So modularity in Nahm sums is like a hidden doorway to this broader world of interconnected mathematical concepts.
Precisely. Now, for a long time, mathematicians believed that there was this beautiful duality relationship at play when it came to the modularity of Nahm sum.
Duality, as in some kind of mirror image relationship.
Exactly. Back in 2007, Zagier, a renowned mathematician, proposed a conjecture known as Zagier's Duality Conjecture. This conjecture suggests that if you have a modular Nahm sum, then its dual, a kind of mathematical reflection term, should also be modular.
So it's all about balance and symmetry in the mathematical universe. It sounds very elegant. But you mentioned counterexamples. So this duality doesn't always hold true.
You got it. The paper we're diving into today presents specific cases where Zagier's duality conjecture breaks down. These counterexamples challenge this long-held assumption about the nature of Nahm sums and their modularity.
Okay, now I'm really intrigued. Let's get into the specifics. What exactly does Zagier's conjecture say, and how do these counterexamples work?
To understand the conjecture fully, we need to look at the formula that defines the dual of a Nahm sum. It's given by AEA, B, A1B, 12, BTA1B, R24C.
Okay, let's break down this formula. What do these symbols represent?
Sure. In this formula, A, B, and C represent the parameters that define a specific Nahm sum. A is a matrix, B is a vector, and C is a scalar. The star symbols like A represent the corresponding parameters for the dual Nahm sum.
So if we input the original A, B, and C, this formula gives us the parameters for its dual.
Exactly. And Zagier's conjecture states that if the original Nahm sum defined by A, B, and C is modular, then the dual Nahm sum defined by the output of this formula should also be modular.
That makes sense. Now, where do the counterexamples come in?
The authors of this paper discovered specific examples of Nahm sum where this duality breaks down. They present a rank 4 Nahm sum that is provably modular, but when you apply Zagier's formula to find its dual, the resulting Nahm sum turns out to be non-modular.
So the mirror image isn't always as symmetrical as we thought? What makes this even more interesting is that Zagier's conjecture wasn't just a random guess. There was compelling evidence supporting it wasn't there.
Absolutely. For instance, the conditions on the matrix A that are believed to be necessary for modularity, those laid out in something called Nahm's conjecture, are invariant under the transformation A1.
So if A satisfies those conditions, so does its inverse, which appears in the duality formula.
Right.
That makes the duality conjecture seem very plausible.
Right. And there's more. The asymptotic behavior of a Nahm sum, how it acts as the variable q approaches certain values Nahm, is closely linked to the asymptotic behavior of its dual. This further supported the idea of a duality relationship.
So finding these counterexamples is a pretty significant discovery. It challenges our understanding of Nahm sums and their modularity. But this paper doesn't stop there, does it? It goes on to explore generalized Nahm sums. What are those?
You're right. In 2023, a mathematician named Mizuno introduced a generalization of Nahm sums by adding an extra parameter D, which is a diagonal matrix. These generalized Nahm sums are written as Fe OEC 2E C O'Hara Ntor Q12 NTAD plus NTB plus CQD1 NE1 NE1 NAT Lixapitor QDR NER.
Okay, that formula looks a bit more complicated. Can you break it down for us?
Of course. We still have our familiar A, B, and C from the standard Nahm sum. The new element D is a diagonal matrix, meaning it only has non-zero entries along its diagonal. The elements of D, represented by D1, D2, and so on, introduce an additional layer of complexity to the Nahm sum.
So it's like taking the original Nahm sum and adding another dimension to it.
Exactly. Mizuno, inspired by Zagier's conjecture, proposed a similar duality should hold for these generalized Nahm sums.
Meaning if you have a modular generalized Nahm sum, its dual should also be modular.
That was the idea. But this paper throws another wrench into the works. It presents counterexamples to Mizuno's conjecture as well.
Double the trouble. How do they demonstrate that?
They start with a specific rank 3 matrix A and a symmetrizer D, along with 3 different vectors, B0, B1, and B2. They showed that the generalized Nahm sum for the combination A, B0, Nagus 148D is modular, while the generalized Nahm sums for the other combinations, A, B, C, D, where I is 1 or 2, are not modular regardless of the value of C.
So they have one modular generalized Nahm sum and 2 non-modular ones. What happens when they apply the duality formula to these?
That's where things get really interesting. The duality formula for generalized Nahm sums is A1, A1, B12, BTAD, A4, A, BT, BA, 21B, Terra2, 24, A, phi D. When they apply this formula to their examples, they get a set of dual quadruples, each with its own A, B, and D. Remember, D is just the same as D.
And what did they find when they examined the modularity of the Nahm sums defined by these dual quadruples?
They prove a theorem 1.3 adapts that leads to some surprising conclusions. It turns out that the dual of the modular generalized Nahm sum is actually non-modular.
Whoa, the duality flipped.
Yes, and to make things even more intriguing, they find that the duals of the 2 non-modular generalized Nahm sums are actually modular.
So the duality works in reverse for those cases. This directly contradicts Mizuno's conjecture, right?
Absolutely. It completely upends the idea of a simple, straightforward duality in this context.
Incredible. How did they actually prove all of this? I'm guessing it involves some advanced mathematical techniques.
You're not wrong. The proof relies on a combination of techniques, including the Bailey pair method, which is a powerful tool for manipulating Q-series identities.
The Bailey pair method sounds intriguing, but maybe we can save the details of that for later. Can you give us a general idea of how it helps them prove these results?
Sure. They essentially establish 4 new Bailey pairs. These are specific pairs of sequences that satisfy a certain relationship and use these Bailey pairs along with some clever manipulations of infinite sums to prove their theorem 1.3, which leads to the counterexamples for Mizuno's conjecture.
It sounds like they discovered new mathematical tools to uncover these hidden truths about Nahm sums. But we mentioned those single-sum Rogers-Ramanujan type identities earlier. How do those fit into the picture?
Those are very important. Theorem 1.4 in the paper presents 4 of these identities, and they play a crucial role in proving theorem 1.3. These identities are elegant in their own right, expressing certain infinite sums as beautiful product formulas.
So they're like little gems of mathematical beauty hidden within this larger proof.
Exactly, and what's even more remarkable is that these single-sum identities, combined with the transformation procedure used earlier, lead to something truly unexpected. Counterexamples to Zagier's original conjecture.
No way. So not only do they find counterexamples to the generalized conjecture, but they also uncover issues with the original duality conjecture.
That's right. Theorem 1.5 presents specific rank 4 matrices A and A, along with corresponding vectors, where the original Nahm sum is modular, but its dual, shockingly, is not.
So the duality breaks down, even in the simpler case of standard Nahm sums.
Yes. This highlights the complexity of the relationship between a Nahm sum and its dual. It's not as straightforward as Zagier's conjecture initially suggested.
This is absolutely fascinating. But before we get lost in the details of Theorem 1.5, let's take a step back and remind ourselves why equation 3.14 is so important. It seems to be a crucial link between the generalized and standard Nahm sums.
You're absolutely right. Equation 3.14 acts as a bridge, allowing us to transform generalized Nahm sums with those extra parameters from D into standard Nahm sums with just A, B, and C. This transformation is what allows the authors to connect the counterexamples they found for Mizuno's conjecture to counterexamples for Zagier's original conjecture.
So it's like a secret passageway between two seemingly different worlds of Nahm sums.
Exactly. And by using this passageway, they're able to demonstrate that the breakdown of duality in one world has repercussions in the other.
This is blowing my mind. Okay, I'm ready for the next level of this mathematical adventure. What else do we need to know about these counterexamples?
Well, you might think that finding a counterexample to Mizuno's generalized conjecture would automatically lead to a counterexample for Zagier's original conjecture, but as the paper highlights in section 4, that's not always the case.
Wait, really? Why not? I thought the generalized conjecture was built on the foundation of the original one.
It is, but the relationship between them is more nuanced than you might expect. The process of transforming a generalized Nahm sum into a standard Nahm sum using equation 3.14 doesn't always preserve the duality relationship in a straightforward way.
Okay, so things are getting even more intricate. Can you give us an example to illustrate this?
Absolutely. Let's revisit those rank 3 matrices and vectors we discussed earlier,
Yeah.
AB0 and so on. Remember when we combined AB0 with the appropriate C and D, we obtained a generalized Nahm sum that was modular, and we discovered that its dual, according to Mizuno's conjecture, was non-modular.
Yes, I'm following so far.
Now, if we use equation 3.14 to transform that original modular generalized Nahm sum into a standard Nahm sum, it turns out that the resulting standard Nahm sum is also non-modular. This is not surprising.
That makes sense. I would expect a non-modular generalized Nahm sum to transform into a non-modular standard one.
Exactly. But here's where it gets interesting. If we apply the transformation procedure to the dual quadruple, the one we obtained by applying Mizuno's duality formula, something unexpected occurs.
Okay, I'm curious.
Yeah.
What happens?
The dual quadruple, when transformed, doesn't actually yield the dual triple we would anticipate, based on Zagier's original conjecture.
So the transformation process disrupts the duality relationship.
You could say that. It's like the mathematical mirror we're using to create these duals gets distorted during the transformation process. The reflection isn't as perfect as we initially thought.
That's fascinating. So even though we have this counterexample to Mizuno's generalized conjecture, it doesn't directly translate into a counterexample for Zagier's original conjecture in this particular case.
Precisely. The relationship between the two conjectures is more intricate than a simple one-to-one correspondence.
Okay, my brain is working overtime to grasp all these nuances.
Yeah.
But this complexity is what makes this topic so captivating, isn't it? It highlights that there's still much we don't understand about Nahm sums and their modularity.
Absolutely. And that's what makes this paper so significant. It doesn't just debunk a couple of conjectures, but opens up a whole new avenue of investigation. What is the true nature of the relationship between a Nahm sum and its dual? Are there any special cases where the duality does hold, but other hidden structures and patterns are waiting to be discovered?
So many questions to explore, but before we get carried away, let's take a closer look at the actual proof of Theorem 1.3. I'm eager to see how those Bailey pairs and single-sum Rogers-Ramanujan type identities come into play.
Let's do it. Remember, the goal of Theorem 1.3 is to demonstrate that the dual of a specific modular generalized Nahm sum is non-modular, while the duals of two specific non-modular generalized Nahm sums are modular. The proof hinges on skillfully manipulating the triple sum that defines these generalized Nahm sums.
Right, that triple sum from earlier. Felon and or euro, Z, RURE, 5, 2R, CRU, RQ12, plus NTB, plus CQD1, D1, N1. It's quite a mouthful.
It is. The key is to break it down strategically. The authors introduce a function f that captures the essence of this triple sum, but with the added flexibility of having variables u, v, and w that we can manipulate. F, u, v, w, f, u, v, w, q, ai, q, q12, I2 plus j2 plus q2, 2w, q, q.
So they're creating a more generalized version of the already generalized Nahm sum.
Precisely. The beauty of this function f lies in its ability to represent the specific generalized Nahm sums we're interested in by substituting appropriate values for u and w.
I see. It's like a master key that can unlock various doors in the realm of Nahm sums.
Exactly. To prove Theorem 1.3, they cleverly manipulate this function f in three distinct ways, each corresponding to one of the three identities they want to establish.
Walk me through how they do that.
For the first identity, they set u and v to q12 and w to 1. This specialization of f, along with some manipulation, allows them to utilize those single-sum Rogers-Ramanujan type identities we mentioned earlier.
So those identities play a crucial role here.
Absolutely. By applying those identities and employing Euler's exponential identities, they transform the expression for f into a form that proves the first identity of Theorem 1.3.
That's impressive. How about the other two identities?
They use a similar strategy, but with different choices for u, v, and w. For the second identity, they set u to q12, v to q, and w to q1. For the third identity, they set u to q12, v to q, and w to 1.
It's as if they're fine-tuning the parameters of this function f to explore different regions of the Nahm sum landscape.
Precisely. In each case, they employ a combination of single-sum Rogers-Ramanujan type identities, along with other Q-series manipulation techniques to transform the expression for f and prove the desired identity.
This is quite remarkable. It's like witnessing a symphony of mathematical concepts coming together. The generalized Nahm sums the duality formulas, the function f. The Bailey pairs the Rogers-Ramanujan type identities, each playing a vital role in the grand composition.
That's a beautiful analogy. And the fact that these seemingly disparate pieces harmonize so elegantly speaks to the inherent beauty and interconnectedness of mathematics.
I'm with you there. But I must confess I'm still a bit unclear about how the Bailey pairs fit into this puzzle. Could you elaborate on their role?
Of course. Bailey pairs are essentially pairs of sequences that satisfy a particular mathematical relationship. The Bailey pair method, developed by W.N. Bailey in the mid-20th century, is a powerful technique for using these pairs to derive new Q-series identities.
So it's like having a specialized toolbox for crafting intricate Q-series identities.
Exactly. In this paper, the authors not only utilize existing Bailey pairs, but also discover 4 new ones which prove instrumental in their proof.
Wow, so they're not just using existing tools, they're expanding the toolbox itself.
That's the hallmark of groundbreaking research. Often you need to develop new methods to tackle challenging problems.
How do they actually utilize these Bailey pairs in their proof?
They combine them with a set of formulas known as Bailey's lemmas, which provide ways to transform Q-series based on the properties of Bailey pairs. By strategically applying these lemmas along with those single-sum Rogers-Ramanujan type identities, they derive the necessary identities to prove Theorem 1.3.
It's truly fascinating how all these seemingly disparate pieces fit together to form a cohesive and elegant mathematical argument.
It is a testament to the power and ingenuity of mathematical reasoning. But we're not done yet. Remember those rank 4 counterexamples from Theorem 1.5? We still need to understand how they arise from the work on generalized Nahm sums.
You're right, we can't leave those hanging. Theorem 1.5 presents those specific matrices A and AA and corresponding vectors that demonstrate the breakdown of Zagier's original duality conjecture for standard Nahm sums.
Exactly, and those examples emerge directly from the insights gained from the generalized Nahm sums. The key, once again, is equation 3.14. It allows us to bridge the gap between generalized and standard Nahm sums. The authors ingeniously use this transformation to connect their findings about generalized Nahm sums to results about standard Nahm sums.
So it's like translating the knowledge from one realm to another.
Precisely. By applying this transformation to those specific generalized Nahm sums that serve as counterexamples to Mizuno's conjecture, they generate specific standard Nahm sums that serve as counterexamples to Zagier's original conjecture.
That's remarkable. The breakdown of duality in the generalized case ripples through and impacts the standard case as well.
That's right. And this further underscores the subtle and complex nature of this duality relationship. It's not a simple universal principle that applies in every scenario. There are nuances and exceptions that we're only beginning to unravel.
This deep dive has been an incredible exploration of the world of Nahm sums and modularity. We've encountered unexpected twists and turns, uncovered hidden connections, and even witnessed the downfall of a beautiful conjecture.
But remember, even when a conjecture proves to be false, it doesn't mean the work was futile. In fact, these counterexamples often provide more valuable insights than the original conjecture itself. They compel us to re-examine our assumptions, refine our tools, and delve deeper into the underlying mathematical structures.
It's like those counterexamples are guiding us towards a more accurate and comprehensive understanding of this mathematical landscape.
Exactly. They're pushing us to refine our maps and explore uncharted territories.
This has been an incredible journey so far. We've delved into the intricacies of Nahm sums, explored the concept of modularity, and uncovered the surprising breakdown of Zagier's duality conjecture.
Yeah.
But we're not finished yet.
Right.
There's still more to uncover.
You're absolutely right. We left off discussing how the breakdown of duality in generalized Nahm sums has implications for standard Nahm sums as well, leading to those intriguing rank 4 counterexamples presented in Theorem 1.5.
Yes, those counterexamples really challenge our understanding of the relationship between a Nahm sum and its dual. So let's dive into the proof of Theorem 1.5 and see how these counterexamples are constructed.
Excellent point. To fully grasp Theorem 1.5, we need to revisit that crucial transformation process embodied in equation 3.14. This equation acts as a bridge, allowing us to move between the realms of generalized and standard Nahm sums.
Right. Equation 3.14 allows us to convert a generalized Nahm sum with all its extra parameters into a standard Nahm sum with just A, B, and C.
Sure.
It's like a mathematical translator.
Precisely. And the authors cleverly exploit this bridge to demonstrate that the breakdown of duality in the generalized case can have profound consequences for the standard case as well.
So they're using the insights from one world to illuminate the other.
Exactly. They begin with those specific generalized Nahm sums that we know contradict Mizuno's conjecture, the ones with the rank 3 matrix A specific vectors B and symmetrizer D.
Right, the ones where the dual of a modular generalized Nahm sum turned out to be non-modular and vice versa.
Precisely. They apply equation 3.14 to these generalized Nahm sums, effectively transforming them into standard Nahm sums. And what they observe is fascinating.
What did they find?
In some instances, the transformed standard Nahm sums are also non-modular, which is not entirely unexpected.
That makes sense. I would anticipate a non-modular generalized Nahm sum to yield a non-modular standard Nahm sum upon transformation.
You're absolutely right. But here's where things take an intriguing turn. When they apply the same transformation procedure to the duals of those generalized Nahm sums, the ones obtained using Mizuno's duality formula, something remarkable occurs.
I'm on the edge of my seat. Tell me more.
Those transformed duals sometimes turn out to be modular standard Nahm sums.
Whoa. So we have non-modular dual generalized Nahm sums transforming into modular standard Nahm sums. That seems counterintuitive.
It is, and this unexpected outcome is the key to constructing those rank 4 counterexamples to Zagier's original conjecture.
Okay, I need to make sure I'm following the logic here. We start with non-modular dual generalized Nahm sums, transform them, and end up with modular standard Nahm sums. How does that contradict Zagier's conjecture?
Let's recall what Zagier's conjecture states. It posits that if a Nahm sum is modular, its dual should also be modular. This implies a kind of symmetry or mirroring in terms of modularity.
Right, the modularity mirror.
Precisely. Now, in these specific cases, we have standard Nahm sums that are demonstrably modular, but their duals, according to Zagier's formula, should correspond to those transformed generalized Nahm sums, which we know are non-modular.
Ah, I see. The transformation process has revealed a discrepancy, a crack in the modularity mirror, so to speak.
That's an excellent way to put it. The transformation acts like a lens, magnifying a subtle mismatch in the modularity between a Nahm sum and its dual.
This is truly mind-boggling. But it also underscores the depth and complexity of this mathematical landscape. These counterexamples aren't just random anomalies, they're pointing to a more nuanced understanding of the relationship between Nahm sums and their duals.
Precisely. They challenge us to reevaluate our assumptions and delve deeper into the intricate structure of Nahm sums and their modularity.
It's like these counterexamples are guiding us towards a more refined and accurate map of this mathematical territory, highlighting areas that need further exploration.
Exactly. They're pushing us to expand the boundaries of our knowledge and venture into uncharted territories.
This deep dive has been an incredible adventure. We started with the fundamentals of Nahm sums and modularity, navigated the complexities of duality conjectures, encountered the power of Bailey pairs and Rogers-Ramanujan type identities, and ultimately confronted the surprising breakdown of Zagier's duality conjecture.
And throughout this journey, we've witnessed how mathematical inquiry is driven by both elegance and rigor, how seemingly straightforward concepts can lead to unexpected complexities, and how even when conjectures are disproven, the pursuit of knowledge yields valuable insights.
Indeed. This paper not only challenges our understanding of Nahm sums, but also serves as a testament to the dynamic and evolving nature of mathematics. It reminds us that even in a field built on logic and precision, there's always room for wonder discovery and the constant refinement of our understanding.
And for our listeners, I encourage you to embrace the beauty and the challenge of mathematical exploration. Never shy away from questioning assumptions, exploring new ideas, and pushing the boundaries of what we know. The world of mathematics is vast and full of wonders waiting to be uncovered.
Well said. On that note, I think we've reached the end of our deep dive. But I have a feeling this is just the beginning of a much longer and fascinating journey into the world of Nahm sums and their mysteries.
Until next time, keep those mathematical curiosities burning bright.
Happy deep diving, everyone.